Section 2.3, Linear Models at our core. In this section, we focus on linear models, which are the basis for many other models, as well as for deep neural networks. Let us consider a feature vector, x, which is x sub 1 up to x sub p, and that's an element of Rp. And the output response variable y, which is a real value. The linear model links the output y to the features x through y equals b plus w transposed x plus epsilon, where the scalar parameter b is called the intercept or bias. The vector parameter w is called the regression parameter or weight vector, and the epsilon term represents the noise or the error. This is a generalization of the simple linear regression model 2.3. So let's look at 2.3 quickly. So 2.3 was up here. Where in 2.3, we used beta 0 instead of b, and w was just a scalar beta 1. So this is a generalization of the simple linear regression model 2.3, allowing x to be a vector. We now denote beta 0 via b. To facilitate the presentation of key concepts of linear models, we often use a more compact representation of the model. So we write y equals the row vector b w1 up to wp multiplied by the column vector 1 x1 up to xp plus epsilon, and that can be just represented as the inner product of the parameter theta and x tilde. So this thing is x tilde plus epsilon, where theta encapsulates both b and w, and the feature vector x is extended to x tilde via a constant unit for its first position. The dimension of theta is the number of parameters, and in this case, it is d, which is p plus 1. In order to use the linear model for prediction of unseen data, we have to learn the model. This means to find appropriate values for the parameters in theta based on training data, such that the model performs well in prediction. Such a suitable learned parameter is further denoted via theta hat. With such an estimated hand, a prediction for the new data point, x star in Rp. So we have a new data point, x star in Rp, is given by y hat of x star is going to be the intercept or bias b hat, plus the inner product of the weights and x star, which is represented here as w hat 1 x1 star up to w hat, this is a typo, p xp. Okay. And that equals theta hat transposed x star tilde. Learning the linear model. Consider a training data set. That's this big D, which is composed of tuples x1, y1 up to xn, yn, composed of a collection of n samples. For such data, it is convenient to define the n by d dimensional design matrix X for the features, and the corresponding output response vector y via. Okay, so this is a design matrix. It is n by d. This is a design matrix, so each column is n dimensional. And with this x, with a superscript in brackets I like this, is the ith feature taken over the n samples. And then the vector y is just as follows. That's the response. Okay. So we put all of the x's in the design matrix, and we put the scalar responses y in the response vector. Okay, that's what's happening here. Using this notation, we can express the linear model for all samples of the training set via y equals x theta plus epsilon, with epsilon equaling epsilon1 through epsilon n representing the vector of noise. So just to check dimensions, see that this makes sense. So we said that x is n by d, theta is d by 1, and epsilon is n by 1, and y is n by 1. Okay? So that is the story here. From this representation, given a learned parameter vector theta hat, we can further define the predicted output vector of the model for the input training data via y hat is going to be x times theta hat. So x is the design matrix actually has the data, and these theta hat would be some learned parameters. Okay. Again, notice that theta hat, this first column here goes for the B, and the second column goes for W1, and the last column for WP, etc. Okay, so theta hat is P plus 1 dimensional. So D is P plus 1 dimensional. Where y hat is just going to be y hat 1, y hat n. A suitable value for theta hat will yield y hat approximately equal to y. This closeness is captured via a loss function. So a loss function is denoted via c, and it's a function of the parameter theta, and it's also given the data. So that's the semicolon data. And the loss function in this case is the arithmetic mean of n separate loss functions, each denoted by ci of theta, where each ci of theta is a ci of theta and of the observation label yi and of the predicted label yi hat. Remember that yi hat already depends on the data as follows. Okay. So the closeness is captured via the loss function. So where ci is the loss for the ith data sample. Specifically, theta hat is typically chosen so that the loss function is minimal at the point theta equals theta hat. Okay, so we're trying to minimize the loss function. For the linear model, the most popular loss function is the square loss function, also called quadratic loss, where for each data sample, what we have is ci of theta is just the difference between your observed label and your predicted label squared. Okay, so that's a square loss. So each one of those CIs, just keep in mind, remember, each one of these goes in here. Okay, so there's a loss for an individual observation and the loss function over all of the data. This loss penalizes each element EI, which is defined as yi minus yi hat, also known as the error or the residual for sample I, quadratically. In this case, the loss for the entire training data can be represented in terms of the L2 norm, so this is the L2 norm, of the corresponding error vector. So the loss for the whole data is the L2 norm squared normalized by 1 on n. We like this 1 on n because it's kind of the average over the individual losses. But that detail is not really important. Okay, so that's the L2 norm of y minus y hat, or the L2 norms of the errors or the residuals. With this notation, by treating the learning of theta as an optimization problem and observing that the objective can be manipulated via monotonic transformations, so you can always do optimization and apply monotonic transformations to your objective without changing your decision. We can now represent the learned parameter vector as, so theta hat is the argmin theta, it's the theta in RD that minimizes your, this is now a vector representation. This is an n-dimensional vector that I'm highlighting here. This is y minus y hat. And this thing is y hat. This is the vector y hat squared. Or you can also get rid of, you can also get rid of this 1 on n, and it's still the same argmin, because that 1 on n is just a constant. Okay. All right. The search for theta that optimizes 213 is known as a least squares problem. Figure 2.5 presents a visual explanation of the squared loss in the case of a single input feature, p equals 1, and hence d equals 2. Okay, so that's a simple linear regression. So what you see in this figure is the 5 data points, and the squared loss is, this is going to be E, and this is E, and this is E, and this is E, and this is E. So this is E squared. So the points B and the points in theta hat B and W1, okay, that minimize this sum of squares would be the optimal loss. So you could visualize in your head this red line moving by changing the points B and W1, right? So the two elements of theta, okay, they determine this red line. And as you move these points, square loss changes, and we're looking for the point with minimal loss. In this case, we seek a line specified by B and W1 such that the sum of squares, total area of the gray boxes in the figure, is minimized, as we said. The least square solution can be easily derived by first computing the gradient of x theta minus y squared. So we want the gradient of this thing, the gradient of this thing. These two expressions, we change the order inside, but that doesn't matter. Okay. So the gradient with respect to theta, and in Appendix A, we have vector and matrix differentiation rules. So this thing is a scalar, and this is a vector. Okay, so this partial derivative representation is a gradient vector of this function from RD to R. Okay. And if you take the gradient, then what you have here, well, first of all, just before taking the gradient, we can just expand the L2 norm squared is just the inner product of these two things. So that's y minus x theta transpose times y minus x theta. And then if you open up the brackets here, open up everything, you got these 4 terms, 1, 2, 3, 4. Okay, so you've got these 4 terms. So then you can, so the gradient with respect to each of those terms with respect to theta, well, this term doesn't have any theta, so it disappears. This term, the gradient with respect to theta is this, okay? And this, sorry, I said 4 terms, but there's 3 terms here because we collected 2 of them with this 2. Okay, and this quadratic form, its gradient with respect to theta is as follows. So hence we have that the gradient with respect to theta equals this expression that you have here. Then by setting the gradient to 0, so a point which is a critical point will have the gradient 0. So equate this thing to 0 and move and divide by 2 and move x transpose y to the other side, you get the normal equations. So these equations for the unknown vector theta are called the normal equations, which describe the vector theta So maybe there's more than one solution. So that's a vector theta that obtain a zero gradient. And in this case, it can be shown that they are global minima of the objective. So see also discussion in chapter 4 about global and local minima. So the Hessian of this function would be positive and negative definite, and then you're going to have a unique global, well, you're going to have a global minimum at a solution, these equations. Sorry, not a global minimum, but also the objective is convex, and hence, and that's why the local minimum is also global. So the normal equations have a unique solution when the D by D matrix X transpose X, also known as the Gram matrix of X, is invertible. So let's still just see the normal equations. So these are the normal equations, and here you have a. So remember that X transposed was X was N by D, so X transposed X is D by D. Okay, so it loses the dimension of the number of observations, but keeps the dimension of the number of parameters. That's X transpose X. So they have a unique solution when this matrix, which is also known just as the Gram matrix of the design matrix X, is invertible. In this case, we can represent the estimator, so we can just multiply by the multiply from the left by the inverse of this thing, and represent the solution, the estimator, as follows, as X transpose X inverse times X transpose Y. Or if we decide to set X dagger as this thing, that's this thing, then we have that theta hat is X dagger Y, where X dagger is actually called the Moore-Penrose pseudo-inverse of X. Okay, so far this is for the case where, let's call it this nice case where X transpose X is non-singular, is invertible. Okay, and we'll speak more about this now. And now we're getting into just a few details, which can be certainly skipped on the first reading. In fact, the Moore-Penrose pseudo-inverse X dagger can be represented in different ways. An alternative form to this way of the Moore-Penrose pseudo-inverse, to X transpose X inverse times X transposed, is based on the singular value decomposition, the SVD of X. Here, then that's the SVD of X. X is U times delta times V transposed, where U is an N by N orthogonal matrix. Delta is an N by D matrix with non-zero elements only on the diagonal. And V is a D by D orthogonal matrix. Now, if you have this SVD, well, any matrix has an SVD, but once you have this SVD, which X has its SVD with the orthogonal matrix transposed, and the, let's call it quasi-diagonal matrix, delta, okay, so it has only elements on its, non-zero elements on its diagonal, but it's not necessarily square. So using the SVD, we can represent the Moore-Penrose pseudo-inverse. So the Moore-Penrose pseudo-inverse can actually be the V from here, a U transpose from here, and with delta, we do a delta plus, where delta plus contains the reciprocals of the non-zero diagonal elements of delta and has zero values anywhere, everywhere else. Okay, so if you have the SVD of the matrix, you can get the Moore-Penrose pseudo-inverse of the matrix as follows. This SVD-based representation holds both if X transpose X is singular, in which case you couldn't get this expression because for singular matrices didn't exist. A situation in which occurs if and only if the matrix X is not a full rank matrix. So that actually the case for X being singular is that the design matrix is not full rank. And it also holds if it's not singular, and you can actually check that if it's in the non-singular case, in the invertible case, these two expressions equal each other. But the point here is that there is a Moore-Penrose pseudo-inverse no matter what. okay? It was all about a discussion about the design matrix. In the singular case, X transposed X is going to be singular if these columns are not linearly independent. But in the, let's call it the nice case, when they're linearly independent, we can just use X transposed X. Okay. So that's it. Note that if X is not full rank, i.e. X transpose X is singular, then there is not a unique solution to the normal equations 215. However, the solution given via 216, so this is always going to be a solution of our least squares estimator, okay, with the Moore-Ponrobe pseudo-inverse sometimes being given like this, sometimes being given via an SVD if we'd like. So, however, the solution given via 216 using SVD form is actually the solution which has a minimal norm for theta out of all possible solutions. Okay. In the context of high-dimensional data, when the number of features P is greater than the number of samples N, the design matrix X is never full rank. This also appears when some of the features are linear combinations of the others, as we just said. If X is mathematically full rank, in some situations there is strong multicollinearity among the features, meaning that some of the features are approximately linear combinations of the others. So even if X is mathematically a full rank matrix, maybe it's practically close to not being full rank because of multicollinearity. And this will yield an X transpose matrix X, so the Gram matrix is going to be ill-conditioned and actually difficult mathematically to invert. In all these cases, the SVD-based representation 217 is useful for using 216 to obtain solution 215. So, then you can use the SVD representation. And anyway, all this has to do where P, the number of features, is not too big, because when P and the number of features is very big, as in deep learning, we typically do not use the Moore-Ponrobe pseudo-inverse anyway. Okay, but in statistical packages, we'll sometimes use this form, and we'll sometimes use this form. Other times they'll use other things under the hood, such as Cholesky factorization and other things. Oh, QR decomposition as well. In all these cases, the SVD representation 217 is useful. Okay. Other loss functions. The first appealing result for the choice of the squared error loss function 212 is a closed form solution 216 for 215. Okay, and again, I'll show it one more time. 216 was this closed form solution here, 216. That's again 216, closed form solution for the normal equations for 215. Okay. Also, when it is assumed that y is measured with uncorrelated Gaussian noise epsilon, using the squared error loss function 212, so the squared error loss function that we used, is equivalent to using a solution derived by the maximum likelihood estimation method, discussed more in the next chapter. This is a technique widely used in statistics for parameter estimation, which is further discussed in section 3.1 in the context of logistic regression. A second popular loss function for the linear model is the absolute error loss. So again, this is a loss Ci for a single observation I, and here we take the absolute error loss between Yi and Yi hat. Keep in mind here that what we're doing is we're actually doing a summation over all features J. Oh, sorry, I'm completely wrong because Yi is a scalar. Okay, so that's just the absolute value. okay, the absolute error loss. It is known to be more robust to outliers. However, in the case of the linear model, there is no closed-form solution for estimating parameters. From a statistical point of view, minimizing the absolute error loss is equivalent to maximum likelihood estimation when assuming a Laplace distribution for the error noise epsilon. The Laplace distribution has heavier tails than the Gaussian distribution. So see figure 216b. So here you have figure 216b, where you have the normal distribution as one, that's a standard normal for some, for the error epsilon, or the Laplace distribution. With these tails, large noise values, i.e. outliers, are more probable than with the Gaussian noise, and hence the loss 218 is typically more robust to extreme values. So just to think about this robustness, the robustness just means that if we have some other point here, right, one point that's maybe extreme and way off the line, it's, you know, it's this error is here bigger than more other errors, it's not probable to have such a point with a normal model, with the normal error model, but it's more probable to have it with the heavier tail Laplace model because there's more mass on the tails. And this Laplace error model is equivalent from a maximum likelihood estimation perspective, even though we didn't speak about maximum likelihood estimation perspective, is equivalent to having the loss function for an individual observation to be the absolute error loss. A third alternative, which is a hybrid between the absolute error loss and the square error loss, is the Huber loss, error loss. It's parameterized by a hyperparameter delta and represented via ci theta is if the error between yi and yi hat is less than delta, then we have kind of a square loss. Otherwise, we have an absolute loss. This loss function penalizes for small errors quadratically and deals with outliers by penalizing larger errors similarly to the absolute error loss. Figure 2.6a provides a visual representation of these three loss functions. Even if it appears to be an appealing trade-off between the absolute error loss and the square error loss, the Huber loss has a disadvantage of having to calibrate the arbitrary extra hyperparameter delta. And like the absolute error loss, it does not have a closed form solution to the optimization problem. Okay, so none of this Moore-Penrose pseudo-inverse for these two other loss functions, for the absolute error loss or for the Huber loss. So here in figure A, you see the squared loss, in figure 2.6a, the squared loss, the absolute loss, or the Huber loss. Okay. Categorical input features. We have so far considered numerical input features. We now describe methods for dealing with categorical input features. The methods we present are useful for linear models, as well as almost any machine learning and deep learning model. Before describing the general method of using one-hot encoding, let us highlight two cases that sometimes receive special attention or treatment. One such case is when the categorical feature is binary. For example, assume the feature that only takes on two values, red or blue. In such a case, it can be encoded via 0 and 1 respectively and used as a numerical variable. A second special case is when the categorical feature is an ordinal variable, which may be interpreted as or converted to a numerical value. For example, if the feature is a user satisfaction rating with values low, medium, and high, it may be transformed to numerical values 0, 1, and 2. Note, however, that this practice is sometimes problematic since different spacings between the assigned numerical values would yield different interpretations of the features and in general yield different models. For example, assigning numerical values of 0, 1, and 4 would indicate a bigger gap between medium and high than between low and medium. So that is all subject to interpretation. Moving on to the general case of non-binary, nominal categorical features, one can use one-hot encoding, a method that we present now. Denote the number of possible values that the feature attains via L. And here, for simplicity, assume the feature values are just 1 up to L. The idea is to create L binary features in place of the categorical feature. If the categorical feature is Z, we construct an L-dimensional vector, Z tilde, which is composed of the indicator 1 of Z equal 1 up to 1 of Z equal L, with 1 denoting the indicator function, taking on 0 or 1. That is, Z tilde is E sub Z, where E sub Z is a unit vector with 1 in the position Z and 0 elsewhere, and it's an L-dimensional vector. See the unit vector notation defined in section 1.6, chapter 1. Thus, each one-hot encoded categorical feature is expanded into such a vector. And with this encoding, the new transformed total number of features is P tilde is P sub n plus the sum of all the I on all categorical features, L sub I, where Pn is the number of numerical features we had, and Li is the number of possible values for each categorical feature I. Okay, so each categorical feature is expanded into Li features. To see how this one-hot encoding affects the design matrix, assume for simplicity that in addition to the Pn numerical features, there is a single categorical feature with L levels. In this case, the n by 1 plus Pn plus L dimensional design matrix is the matrix which you have here. It's a matrix with still the column for the bias vector, and you have Pn columns, 1 for each Pn, and then in our case, the one categorical feature was expanded into these L additional columns, where all of these, where these are one-hot encoded. So that means that each vector here has only a single 1 at some point, and otherwise is all zeros, and it's 1 for the value of that observation, right? Because the rows are observations. Here, Z tilde sub j, for j equals 1 through L, is the vector of indicator variables that marks which observations are at level j for the categorical feature. In statistics, the new L columns, Z tilde j, are called indicator or dummy variables. However, in statistics, the practice is to include only L-1 dummy variables instead of L. One reason for this is when using L dummy variables, the design matrix X will never be a full rank matrix, since the sum of the L dummy columns is equal to the first column of 1s. Thus, traditional statistical practice only includes L-1 dummy variables in the model, and the remainder is considered as a reference level. But keep in mind, in machine learning, that's not so important, especially if you have P very large, P much larger than N, in which case X is anyway not full rank. An alternative is to remove the bias term from the model, meaning drop the first column of X, and then keep all L dummy variables. Just keep in mind that when you see one-hot encoding in statistics, you typically use L-1 levels, not all levels. Multi-class classification. Now that we understand the linear model, as well as ways of dealing with categorical variables, let us consider an application of the linear model for multi-class classification. We note that linear models are generally far from the state of the art when it comes to their application for classification problems. Yet seeing the linear model applied to classification is instructive. In classification problems, each of the labels y takes on one of a finite number of values. The number of possible values is denoted via k. When k equals 2, it's a binary classification problem, but generally for k greater than 2, it is a multi-class classification problem. Notationally, it's convenient to denote the set of labels indices as 1 to k, and consider some bijection between these indices and actual values, example, banana, dog, etc. As a concrete example, we consider the MNIST dataset, where the label values are the digits 0, 1, up to 9. And notationally, we use label indices 1 through k, where k is 10. Here, the obvious bijection shifts by 1. A general scheme for multi-class classification is introduced in section 3.3 in the context of multinomial softmax regression, and is further employed with other deep learning models in the chapters that follow. An alternative which we introduce now in the context of linear models, but it's not just limited to linear models, is based on the fusion of multiple binary classification models into a multi-class classifier. For this, we introduce two general methods, namely 1 versus all, and that's also known as 1 versus rest, and 1 versus 1. So 1 versus all and 1 versus 1. Both of these methods assume we have trained binary classifiers for subproblems. With the 1 versus all strategy, we assume the availability of models for binary classification f theta I, for I 1 through k, where the ith model can discriminate between the label index I treated as positive, and otherwise a label index not I is negative. So each of these models, f theta I, is just for label I. It says, is it a label I or is it not? With the 1 versus 1 strategy, we have more, k times k minus 1 binary classifiers, denoted f theta ij for all ij pairs, such that I not equaling j. Okay, so this is a number of ordered pairs which you have. In the footnote here, you have, in practice, you can get half of those because you can, a classifier that distinguishes between I and j is like a classifier that distinguishes between j and I. But that's a detail. Here, the ijth classifier discriminates between the label being I or j. Okay. The output range obtained by f theta I or f theta ij is generally a value on the real number line R. Positive outputs indicate positive, while negative outputs indicate negative. The farther the model output is from 0, the stronger the confidence of the classification decision, whether it be positive or negative. A cutoff in similar nature to 2.5, so 2.5 was a threshold cutoff, which we had in the previous section, is to apply the sign function to the model output and conclude either positive in case of positive 1 or negative in case of negative 1. Now the 1 versus all and 1 versus 1 strategies can carry out prediction via the following. So here you have the strategy. So the prediction of 1 versus all is going to use your capital K models and is going to do the argmax, the model that actually maximizes that label over all other labels. The prediction for 1 versus 1 is more complicated because for every label I, we're going to sum over all the j's, the signs, comparing the models f theta ij over all other cases. The idea of the 1 versus all strategy, so let's read it. The idea of the 1 versus all strategy is to pick the label index which is most probable among the K classification models, where each model focuses on a different label index. Okay, so that was the one versus all. That's this guy. The idea of the one versus one classifier is to pick the label I that when compared to the other k minus 1 labels was chosen most often. This is achieved via comparison of a summation of sine f theta ijx for all other labels j. In both cases, one needs to supply rules for handling ties in the argmax in the final decision, yet these details are generally insignificant. So you'll actually think a bit about the one versus one case. All right, so this case, it's a bit involved, but it's nice. So you have all these classifiers that classify between I and j, and for every I you count this, and as we said here, the label I that when compared to the other k, we're picking the label I that when compared to the other k minus label was chosen most often, and that's obtained via this summation. We proceed with an example of using both strategies for the MNIST dataset using the linear model. The crux in creating the supporting binary classifiers is to set the label vector y used in 216, so we'll see 216 in a second, to have values of +1 for samples that are positive and values of -1 for samples that are negative. So let's go to 216. So each time we're just going to do an estimation as follows, but every time for binary classification. And each time what we're going to do is we're going to set the labels y to be either +1 or -1, depending on the classifier that on the model that we're currently training. Okay, so there are going to be many binary classifiers or multiple binary classifiers at play here. For example, when learning the f theta 3 classifier, so that's a classifier if a digit is label 3 or not, okay, where label 3 is actually label value 2 because we shifted from 0 to 9 to 1 to 10. For example, when learning the f theta 3 classifier, we consider all digit images in the original dataset with the label value 2. Okay, and the footnote explains why it's 2 and not 3. It's having y equals +1 and otherwise -1. Out of the 60,000 MNIST training samples, there are 5,958 training samples that satisfy y +1, and then for y -1, that we have the remainder of samples. Obtaining the parameters for this classifier using 216 uses a design matrix X as in 210, which is of the dimension 60,000 by 785, right? So we have 60,000 observations and 28 squared, which is 784, plus 1 makes it 785 for the box. That 785 is 1 plus 28 times 28. Each row of X corresponds to a different image, and each of the columns 2 to 785 corresponds to a different pixel. Similarly, when learning the f theta 38 classifier, this compares the digit 2 and 7, right? 38 is label index 3, label index 8, which is digit 2 and digit 7, used in the 1 versus rest. This is a mistake. That's the 1 versus 1 case, right? The 1 versus 1 case, not the 1 versus rest case. Using 1 versus 1, we set +1 for all 5,958 training samples that have 2, and set -1 for all the samples that have a label 7, and there's about 6,265, no, exactly 6,265 of those. Here the design matrix X is of dimension of the sum of these two things, so it's not going to have as many observations, the design matrix X, because this classifier is only trained as a binary classifier to distinguish between 3 and 8. Here the design matrix, or between 2 and 7, you can say. Here the design matrix X is of dimension as follows. Okay. To obtain predictors theta hat I or theta hat ij using 216, 216 was the pseudo inverse solution to the least squares problem. We compute the pseudo inverse of the respective design matrices using, for example, numerical procedures for 217. Okay, numerical procedures for SVD, for example. Note that the theta hat I classifiers require only a single pseudo inverse, while theta ij have a different design matrix for each ij pair and hence requires its own pseudo inverse. Now, after training on the 60,000 MNIST training samples and evaluating performance on the 10,000 testing samples, we obtain an accuracy of 0.86 using 1 versus all, and an accuracy of almost 93%, that's 0.9297, using 1 versus 1. As MNIST is a generally balanced data set, the use of accuracy to evaluate performance is sensible, and the level of accuracy obtained is impressive since the linear model is very simple and training these models using the pseudo-inverse computation only takes a few seconds at most. However, to get industrial-grade performance, one requires more advanced models, such as the convolutional neural networks of Chapter 6, where we certainly won't use the pseudo-inverse. As mentioned in the previous chapter, state-of-the-art performance for MNIST is at an accuracy of over 99.8%. When evaluating multi-class classifiers, it's common to use a confusion matrix similar to the 2x2 confusion matrix presented in the previous section for the case of binary classification. So table 2.1 presents the confusion matrices for both 1 versus all and 1 versus 1. It's insightful to pick out the entries where non-negligible misclassification occurs. For example, with the 1 versus all classifier, multiple real digits of 7 were classified as 9. This occurred 77 times. We'll see this in a second. Similarly, in the 1 versus 1 case, there were 36 misclassifications of the digit 5 as a digit 8. So here in table 2.1, you have in A the 1 versus all, and in B the 1 versus 1. Okay, so first of all, just note that your accuracy is going to be the sum of the elements of the diagonal divided by the total number of observations, which in this case is 10,000 in the test sample, right? So the heavier the diagonal, the better. And then there were some statements in the paragraph about specific misclassifications in this table that stand out. So where was that specific case that stood out? Let's go again to the text. So for example, with the 1 versus all, the real digit 7 classified as 9. So in reality, if you've got 7 classified as 9, okay, so there are 77 cases like that. And this is an indication of, oh, okay, our classifier, well, we need to be careful that 7s are often classified as 9. And that is it. There was a whole lot in this section. This concludes section 2.3. We hope you enjoyed this video and found it useful. As always, let us know what you think in the comments below. Thank you. Bye-bye.